During this segment, we will talk about complex numbers. When we've come up with things like the square root of negative numbers, such as the square root of negative 81, we have said that this is not a real number. And that is a true statement. But if we expand the real number system to include what we call the imaginary unit, then we can simplify some of these expressions. Let's look at the following. This is what we call the imaginary unit. We define the imaginary unit, written I. It's the number whose square is negative 1. That is, now it's very important to know these, I squared equals negative 1, and I equals the square root of negative 1. So let's see how we can simplify an expression such as the square root of negative 81. Well, do you agree this is the square root of negative 1 times 81? And then I can write this as the square root of negative 1 times the square root of 81. What is, by definition, the square root of negative 1? It is I. And what is the square root of 81? It is 9. So this is I times 9, or 9I. There, I've simplified that expression. What about, for example, the square root of negative 7? Well, that is the square root of negative 1 times 7. So it is the square root of negative 1 times the square root of 7. The best I can do is write this as I. So this is I times square root of 7, or just I square root of 7. And then let's simplify one more expression before we look at another definition. Let's suppose I have the square root of negative 24. You can just simply remember that this is the square root of negative 1 times the square root of 24. So it is I times the square root of 24. Then look for any perfect square factors of 24. Well, I know 4 is a perfect square factor of 24, and 4 times 6 is 24. So this is I times 2 by the product rule times square root of 6. And I'll write that as 2I square root of 6. So a little simplifying there. Now let's look at a definition of a complex number. A complex number is a number that can be written in the form a plus bi, where a and b are real numbers. Let's continue simplifying, but I want you to be aware that the product rule does not always work for imaginary numbers, an imaginary unit. For example, the square root of negative 5 times the square root of negative 10, we need to simplify each of these radicals separately before multiplying. So, for example, let's just deal with the square root of negative 5. Well, that's the square root of negative 1 times the square root of 5. So that's I square root of 5 times, concentrate on the second radical, that's I square root of 10. I square root of 10. Now we're taking the square root of a positive number, square root of a positive number. Now we can use the product rule. So this is I times I, which is I squared, and then times the square root of, what is this, 5 times 10? 5 times 10 is 50. Now we're just continuing now to simplify, but notice I did not use this part of the product rule until I had non-negative radicans. Now let's deal with the square root of 50, and let's deal with I squared. By the way, how did we define I squared? I squared is negative 1. I squared is negative 1. And then does 50 have any perfect square factors? The answer is yes. 50 is 25 times 2. So this is -1 times, and then by the product rule you can separate these two as the square root of 25 times the square root of 2. Square root of 25 is 5, and then we do have the square root of 2. And then look what we have. -1 times 5 is -5 square root of 2. This product is -5 square root of 2. Now let's see how we add or subtract complex numbers. Sum or difference of complex numbers. If a plus bi and c plus di are complex numbers, then their sum is, here I have a plus bi plus c plus di is equal to a plus c plus b plus d times I. Their difference is, notice here I have a plus bi minus c plus di in parentheses, and here I have finally in parentheses a minus c plus in parentheses b minus d times I. Now that actually looks harder than it really is. I found that for students, and notice here I am adding two complex numbers, it might be easier if you just for a moment, even though this is not true, kind of think as I as a variable and treat this as a binomial plus a binomial, and then remembering how you combine like terms, you will be just fine. But always remember that I is a constant. It is the square root of -1. So let's just take off parentheses for minus 7i plus 2 plus 3i, and then look for like terms. 4 plus 2 is 6, and then -7i plus 3i, that's -7 plus 3, and that's -4i. And these are, if you want to think of it this way, kind of unlike terms. So here I have a complex number plus a complex number. The sum is a complex number. It will work that way every single time. So I've added complex numbers. Now let's subtract complex numbers. I have the complex number 6 minus the complex number 8 plus 4i. Now notice I called that a complex number. It is a real number, but it is also a complex number. We've just never introduced the complex number system. So I'm subtracting these two numbers. Do as usual, take off parentheses, and that's 6. And as usual, use the distributive property, minus 8 minus 4i. Well, these are what I'll call like terms. 6 minus 8 is -2, and then minus 4i. And then notice I can go no further. I cannot combine these two. So I subtracted two complex numbers. I have a complex number. Let's now take a moment and let's now multiply complex numbers. Let's suppose I have -10i times -4i. There we go. Again, just think of it for the moment. Think of I as a variable, but it is not a variable. It is a constant. How would I multiply -10x times -4x? Well, -10 times -4 is 40, and then I would have x times x, x squared. Here I have I times I, or I squared. Perfectly okay, we're just not simplified enough. If you ever have I squared, remember I squared is the same as -1. So I have 40 times I squared is -1, and so this becomes -40. This product is -40. Let's continue to multiply. Let's multiply the complex number 6 minus 2i, that's a complex number, times that complex number 3 plus I. If it helps, you might want to think of it as a binomial times a binomial. So let's go through and use the FOIL order of multiplying. And we are, by the way though, multiplying complex numbers. First times first, 6 times 3 is 18. Just be careful. 6 times I, that's 6i. Then the inner product, negative 2i times 3, that's negative 6i. And then last times last, negative 2i times I, now that's negative 2. And then what's I times I? It's I squared. So I have 18. These are like terms. Not only are they like terms, but they subtract out. So those two terms are gone. Minus 2 times, what do we write instead of I squared? I squared equals negative 1. So I write negative 1. So this is 18 minus 2 times negative 1 is negative 2. And what is 18 minus a negative 2? That's 18 plus 2, or 20. We multiplied these two complex numbers, and we just happened to get the real number 20. Now let's look at the following definition, reminding us of the definition of a conjugate. This is what we call complex conjugates. The complex numbers a plus bi and a minus bi are called complex conjugates of each other. And a plus bi times a minus bi equals a squared plus b squared. Now, why did we talk about complex conjugates? Because we are now about to divide complex numbers. We added them, we subtracted them, we multiplied them, now we are dividing them. As a matter of fact, I'd like to divide these two complex numbers and write the answer in the form a plus bi. So how do we do that? Well, it's kind of like when we were rationalizing denominators and the denominators were binomials. That's what it's like. I'd like for the denominator to be a real number in order for me to write in the form a plus bi. To do that, I will multiply numerator and denominator of this expression by the conjugate of the denominator. Now, what is the conjugate of 1 plus I? It is 1 minus I. So multiply numerator and denominator by the exact same thing, 1 minus I. Same thing as multiplying by a form of 1, but let's see what this does. Watch what happens in the denominator. Think of this as a binomial times a binomial, and I have 1 times 1, which is 1, watch, minus 1i, plus 1i, and then last times last, minus I squared. I'll simplify that in a moment, but let's go ahead and do the same thing in the numerator. Let's multiply. First times first, 3 times 1 is 3, minus 3i, inside product plus 5i, and then last times last, minus 5i squared. Now we will just be simplifying. In the numerator, if you want to start there, that's 3. I have these like terms, which I'll call them that. Negative 3i plus 5i, that's plus 2i, and then be very, very careful. Minus 5, then I squared is negative 1. Do the same thing in the denominator, but something special happens in the denominator, and that is that the middle terms subtract out or add out, however you want to think of it, and I have 1 I'm writing down that minus sign, and then I squared is -1. Now we are just simplifying. So I have, now this is 5, correct? -5 times -1, that's 5. 5 plus 3 is 8. So I have 8 plus 2i in the numerator, and then that's 1 plus 1, which is 2. So I have 2 in the denominator. What I can do now is the following, and it really depends on you as to how you want to do this. I can factor out a common factor of 2 in the two terms in the numerator, then divide out, or if you'd like, you can take each term in the numerator and write it over that one term in the denominator. And I can do it because there's just one term in the denominator. So it's 8 over 2 plus 2i over 2. That's how we actually write it in the form a plus bi, but it just so happens here things simplify. So finally, this is 4 plus I. They won't always simplify completely out like that so that I have no denominator or no fractions, but in this case it happened. So I divided those two complex numbers, and I have the complex number 4 plus I as the quotient. Now let's take a moment and let's look at a unique pattern when we look at powers of I. Let's look at some powers of I and let's see what happens. Now I know I is just I. What is I squared defined to be? I squared is -1. Now watch what happens. I'm going to increase the power of I. We'll look at I cubed. Do you agree that I cubed is I times I squared? So I have I times I squared is -1. What is -1 times I, or I times -1? That's -I. So it turns out that I cubed is simply -I. I'm about to erase all this. I cubed is -I. What is I to the 4th equal to? Do you agree that I to the 4th, one way we can think of it is I squared times I squared. Well, this is -1 times -1. What's -1 times -1? It is 1. Believe it or not, I to the 4th power is simply 1. Continue. What is I to the 5th? Well, since I to the 4th is 1, I'm going to write I to the 5th. There are many ways I can write it. I can write it as I squared times I cubed or other ways, but I'm going to write it as I to the 4th times I because I know I to the 4th is 1. So I have 1 times I, which is just I. I to the 5th is the same as I. Now, I'll just write down a few more of this pattern, but I won't go through and show you. You can work it out yourself. I to the 6 turns out to be, now watch what happens. I have I, -1, -I, 1. I know this is -1. I know I to the 7th is -I, and I know I to the 8th is 1. That pattern just continues and continues. So let's use that pattern. I'll just keep the first 4 powers, and let's evaluate some higher powers of I. For example, I had it written a moment ago, but if I asked you to evaluate what is I to the 8th power, you got one of 4 answers anyway. It's either going to be 1 or -1 or I or -I. In this case, use as many powers as I to the 4th as you can using the power rule Do you agree that that is I to the 8th power? The answer is hopefully yes, because 4 times 2 is 8. This is then 1 squared, which is 1. I to the 8th power is 1. As a matter of fact, if your exponent is divisible evenly by 4, the I to that power is just going to be 1. Let's evaluate one more power of I. Let's suppose I have 2I in parentheses raised to the 6th power. Let's use our rules for exponent. This is 2 to the 6th times I to the 6th. All right, 2 to the 6th, 2 times 2 times 2 times 2 times 2 times 2. I'll let you work it out, but that is 64 times I to the 6th. Well, I to the 6th is I to the 4th times I squared. I to the 4th is just 1. And then what is I squared? Negative 1. So I have 64 times 1 times negative 1. That is negative 64. This evaluates to negative 64. It all comes from this unique pattern occurring with successive powers of I. At this time, practice working with complex numbers. Let's talk about how your homework assignments are going, and to do so, let's ask the following question. What does it mean to complete a homework assignment? Well, to complete a homework assignment, first of all, attempt all of it. If you are given a certain number of exercises to try for homework, make sure you attempt all of these. In other words, just because you cannot or you have trouble working number 5 does not mean you'll have trouble working number 7. So don't give up if you have trouble with 1, then leave it alone and continue on. Make sure you attempt all of your assigned homework. After that, make sure you check it. Now, if you are given odd exercises, the answers to odd exercises are in the back of your book. So definitely check any odd exercises given as homework. After you check it, there's no sense checking it unless you plan on correcting it. So if you did get a wrong answer and you know it by checking, make sure you correct it, or at least attempt to correct it. If you're still having trouble, just put a question mark by that exercise, reminding you to ask questions about it during your next time with your instructor. And then finally, do ask questions. Again, any homework exercises that you have trouble with, you might want to put a question mark by them, and that is to remind you to ask questions about it. Whether you ask questions of your instructor, or you go to a learning resource center, or you look at lecture videos, whatever you need to do to help you through your learning process. So good luck with your homework assignments.